So let's talk about the Diekmann reaction. And the Diekmann reaction here is kind of an internal carbonyl attack. It's going to be very analogous to what we see with like Robinson annulation and reactions like that. But this is a special class where we have this symmetric ester. So there's a diester, kind of a little nuanced reaction, but it does come up. And the reaction conditions here is that we have the alkoxide, which is the alcohol equivalent of whatever's bound to this ester. And the reason we need to use an alkoxide that is the same as these RO groups here is because these alkoxides will also attack the carbonyl, and what we don't want is to start swapping off what those R groups are. So if this is an ethyl group and we use a methyl group, not only will we get the Diekmann product, we'll also get the ester with different R groups on it now because we're getting that reaction. But what we need here is a really strong base. So if we use hydroxide, this will convert these to carboxylic acids. We don't want that. Instead, we're going to use the alcohol. What the alcohol is going to do is it's going to abstract the hydrogen from an allylic carbon. So again, we're going to stay simple here. We're going to focus on basically symmetric diesters. You can do this with asymmetric. You would get a mixture of both depending on which allylic carbon you work with. But we need the allylic carbon. And what this allylic carbon is going to do is it's going to attack the carbonyl carbon and break off one of the esters. And if we work out the reaction products, I'm just going to kind of write them off here to the side here. This is 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5 carbons. And 1, 2, 3, 4 carbons. And so let's number the carbons. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 1, 2, 3, 4. So what's bound to this first carbon here is the other half of the ester. So for all these, we're going to end up with an ester on one side. And when we get done, because we're basically using this to knock off the other end of the ester, the last carbon, the one that's adjacent to the first carbon now in the ring, this is going to end up getting carbonyl. So the end result of a Diekmann reaction is you form either a cyclohexane, a cyclopentane, a cyclobutane, whatever number of carbons are necessary to like kind of form this ring between the allylic carbon and the other ester. You're going to end up with an ester group and a ketone on the ring. Now, this is a nice, simple internal reaction. The driving force here is cyclization. You're probably not likely to generate a lot of small rings, and you're probably not likely to generate very large rings by merit of the fact they're not that stable. So this reaction is pretty preferable if you want to make the 6 and 5 membered rings. But that's the overall picture of how you do a Diekmann reaction. Again, if you do something asymmetric, so let's say we put a methyl group here on the last carbon or the adjacent carbon, you would need to consider both products, one where this is losing the hydrogen, one where this is losing the hydrogen, and you would just end up with a mixture when you were done.